So current is dealing with the flow of positive charge. Remember Ben Franklin, talked about, what they thought static electricity was coming from glass versus, rubber or resin. And the convention is stuck, and we've stuck with the current being the flow of positive charge, even though really it's electrons going the other way. We calculate current by taking the charge that passes by in a certain amount of time, and we get current in amps. Now, if electrons are going this way, we know that current, therefore, is going the other way. And inside a conductor, we know that electrons move, randomly and not smoothly as they go through. And that should kind of make sense because you got electrons and electron clouds whizzing around, and they're not going to go in a straight path. Now, once an electric field is established in a wire, you have electrons passing through. What we're going to do in this case here with this problem, we have a voltage set up, an electric field is set up inside the wire, and this is going for an hour. We have 11 milliamps. And the question for this one is how many electrons per hour pass by? Now, this will be a good chance to practice using your equation sheet and looking for the stuff that you need. So yeah, go ahead and pause the clip and go ahead and find what you need there. And when you're ready to check these, you can hit play to continue. All right, so 41 coulombs will be going by in 3,600 seconds. And we needed to convert our milliamps to amps. And we've got our time here in seconds. And so 41 coulombs is passing through. And, we take the total amount, 41 coulombs, divided by the charge of 1.6 times 10 to the negative 19th. And we get a lot of electrons. It's going to take a lot of electrons to get 41 coulombs of charge. If the electrons are moving north, the direction of the current is moving south. All right, so now we're going to take a look at the derivation of the wire here with current. So, once you set up an electric field inside, let's say all these are electrons, you establish a field inside and they're going to start to move. Now, they're all not going to move in the same direction, but they're going to move in the general same direction because of the electric field. They're going to be more zigzaggy, right, as they go through and then make their way, okay? Now, they're going to cover a certain distance in a period of time based on how fast, the drift speed. So V is delta x over t, we know that, and so V times t is going to be equal to delta x, and how far it goes will be based on the drift speed times the time that it takes to go across. Now, let's say that in a given amount of time, these particles will make it past this area in a certain amount of time. Well, we can use that to further look at what's going on with current. Now, drift speed is the speed at which the electrons move opposite to the direction of the electric field in a given amount of time, and and again, it's going to be zigzaggy as it goes. Now, what we're given here in the information here, we know that the current is 1 amp. We have the radius, which is 2 meters or 2 millimeters, and then we have how many electrons per unit volume. So if we have a volume of 1 meter by 1 meter by 1 meter like this, and 1 meter, 1 meter, 1 meter, inside here are 10 to the 28th electrons. Now, inside this little wire here, you don't have nearly as many, but we can use this. This is N, which is the number of electrons per meters cubed, and we can use that if we know something about volume. So what we're going to do here, this is the area, and we have each charge is Q, and it's going to be passing through this area. We know the current is how much charge in a period of time. And we also know here that length is V times t, right? So the drift speed times the time. We're going to be able to get the length that it travels. So if we know the length that it travels and we know the area, that's essentially volume. And if we know what's going on with volume, we know this is, how many electrons there are in per volume, right? And so that's essentially where we're going here. All right, so what we're going to do then is take the V times T times A, which is the volume of this thing, which is, in meters cubed. And then we're going to multiply that by N, which is the number of electrons per meters cubed. So what's going to happen is meters cubed is going to be gone, and we're going to have how many electrons are actually in here that are going to pass by. And then if we multiply that number by Q, we're going to get how much charge actually passes through. And then what we can do is we can take this and put it all into here. And when we do that, the times will cancel out. And then we're left with the drift speed times the area times N times Q. And this is the current that passes through. And so yeah, I'll go ahead and pause the clip and solve for the in this case here, we're looking for the drift speed. What is the drift speed based on all these values? And so yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so we should get here 4.97 times 10 to the negative 5th meters per second. Now that can seem very, very slow. And so the question that I've got for you now is, why does it take a long time for a light bulb to come on, when you turn the switch on? Well, if you think about it, there's electrons located all throughout that circuit. And so as soon as you set up that potential, as soon as you set up some voltage, that charge is going to start to move through. And that's what we see there. Okay, another thing that we talked about was critical from today, ohmic versus non-ohmic resistors, right? So if you have a wire, just a typical wire, a copper wire, right? It's ohmic. That means that no matter what you hook this wire up to, it's going to have the same resistance, whatever that is in ohms, right? Whatever you got, okay? Now, that follows this kind of pattern where, you're increasing voltage, current's going to increase at the same rate according to V equals IR, right? Now, with this is dealing with a situation like a light bulb. A light bulb does not obey Ohm's law. As you get higher and higher in voltage, you can see how the current is actually tapering off. And so even if you go higher voltages here, the current's not getting very much higher. And so that's important there. All right, so on your equation sheet, it looks different than this. It turns out on your equation sheet, it's in terms of rho. It gives you rho is equal to the rest of it. Now, I like rearranging it and thinking about it this way, looking at resistance of an object based on its geometry, because I can kind of see it. Resistance is equal to rho times L over alpha. Okay. Now, that means that if you have a longer wire, there's more resistance, because that current, those charges have to pass through a longer wire. Now, if you have a greater area, if the area is greater, resistance is going to be less. This is in the denominator, and therefore, the resistance will be less. And then the smaller the resistivity, copper is going to have a smaller resistivity than aluminum. Gold's going to have a better resistivity than copper, right? So, yeah, so that's what we're dealing with there. Now, here's each of these values. Resistivity is in ohm meters, length is in meters, cross-sectional area is in meters squared, resistance is in ohms. So let's go ahead and practice this one here. What is the resistivity, which is rho? What is the resistivity of the substance that has a resistance of 1,000 ohms if the length of the material is 4 centimeters and its cross-sectional area is 0.2 centimeters squared? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so yeah, we're going to convert to meters. We've got 100 centimeters, so we're squaring both. We have 100 squared centimeter squared is 1 squared meter squared, and so we get our area is 2 times 10 to the negative 5th. We'll solve for our resistivity, which is 0.5 ohm meters. And so that's for this particular substance. All right, this is a good chance to practice another section here where this is very important as well. We have a 100-watt light bulb, 120-volt DC power supply, and we want to find out how much current is flowing through, and then we want to find out the resistance. Now, this is a good opportunity to use your equation sheet to practice this as well. So yeah, go ahead and pause the clip and give us a try, and when you're ready to check, you can hit play to continue. All right, so we're dealing with 0.833 amps. This is wattage, which is power. This is voltage, which is V, and we're looking for I. current. 0.833 is what's going through. We can use Ohm's law and figure out the resistance. Now, this resistance of 144 ohms is for this particular voltage. Because this does not obey Ohm's law, let's say we put 60 volts on this thing, it's actually going to have less resistance if it's a light bulb. So it's important to keep that in mind, whether the object is ohmic or not. All right, so the last step here that we're going to look at, and this is a critical thing that we looked at a lot this year, is a series circuit. We have a 4 ohm, we have an 8 ohm, we have an 11 ohm resistor. Now, in class, we pulled up the FET simulator, and it might be worth for you doing that. Pull up, you just Google search circuit construction kit DC only, and you can pull this up and make one. But what we saw is as the current passes through here, it's all going at the same rate. It takes the same amount of time as it goes and goes and goes and goes all the way around. And therefore, current stays the same in series. Okay? Current staying the same in series. So, what I'm going to have you guys do in this one, if you remember what to do, we're going to have to bring these all together. Once we bring them all together, like one bulb instead of many bulbs, we can apply Ohm's law. And then we're going to reconstruct and figure out how much voltage each of these uses, as the current goes through. So go ahead and pause the clip and give that your best shot. And when you're ready to check, you can hit play to continue. Okay, so we get them all together, should get 23 ohms. Remember, it's R1 plus R2 plus R3 equals the total resistance in series, which is 23. So 23 ohms, V equals IR, and we should get 0.26 amps. Then when we break it apart and we get each of them, we get 1.04 for the first, 2.86 for the second, and 2.08 for the third, because we apply Ohm's law to each, and we can figure out how much voltage it uses. And if you remember that analogy, the voltage river uses up a certain amount per resistance there.